Thank you, Nathan. So, my name is Josh Lewis. I'm the Energy Group Manager at S&P Technical Services. S&P is a full-service engineering consulting firm headquartered here in Windsor with operations throughout Ontario and the United States. We have three primary divisions in our company, the Energy Group, which I run, a Facilities and Process division more focused on industrial manufacturing, and then we also have a Building Group. So we do bring the full suite of engineering services under one banner, and we work with our valued clients and partners to offer full service solutions to our clients. I'm a University of Windsor alumni, electrical engineering. I'm also a certified energy manager and a certified measurement and verification professional. It was working. There we are. So S&P is proud to be sponsoring this event. I encourage you to stop by our table out there at the coffee break after this session. And we have a slogan for our energy group: conserving energy creates new revenue streams. So we look at energy efficiency as a way that companies, commercial and industrial, even residential, can really increase their revenue through energy conservation. So as many of you know, energy efficiency has been shown to be cheaper than building new generation, and it's certainly better for our environment. So we really look to energy efficiency as a way of going forward, and we don't think it's ever going to stop in the next 100 or 200 years, unless somehow we can generate free or very cheap energy like through nuclear fusion and we have a technological shift. Until then, energy efficiency is going to be foremost. One example, just in terms of relating it to revenue. So anybody who knows about net margins in businesses, if you look at like the food industry, grocery stores, they're typically running at very low net margins, maybe 2%, 2% of gross sales. So a $20,000 a lighting retrofit at a grocery store that saves them $20,000 a year in electricity is the equivalent of that grocery store selling $1 million more of groceries in that year. That's a huge difference. Most grocery stores could never imagine selling $1 million more worth of groceries, but doing a lighting retrofit has exactly the same effect. And we use that as a selling feature a lot of times when pitching projects to show people how energy efficiency really contributes to revenue. So I'm here today to talk about the 7 types of energy losses. So this is practical. We use this every day. We've audited hundreds and hundreds of millions of dollars of energy usage throughout in commercial and industrial businesses. And we use these 7 types of energy losses to quantify the waste within these energy audits that we do. So my goal today is to bring you a new perspective on how to think about energy losses from a real practical sense. Provide a framework to understand, classify, quantify, and address those losses, and then improve the efficiency of your efforts to reduce energy losses within your equipment, process, facility, or even within your research. So before I get into the losses, let me just tell you how this kind of unfolded and how we kind of came across this over the last 7 to 8 years. A large part of the energy auditing that we do are what we call energy cost deployments rather than energy audits. The difference being that our energy cost deployments are a dynamic model of energy usage within a facility or within a building rather than a static snapshot. Okay? So we typically do these energy cost deployments, we base them on a 12-month period, but they can be updated regularly to roll the model forward, okay? Whether we do that on the client's behalf or the client does that themselves. So to roll a model forward, you typically have to update the billing, the metering, with the internal metering data, the weather, and the production or occupancy data of your facility. And if you update those on a monthly or bi-monthly basis, you can roll the whole energy cost deployment forward. So it's kind of like a living energy audit. But it can also be adjusted as to regularly reallocate the distribution of the energy usage within your facility based on changes you've made. You might have made operational changes. Maybe you're shutting air compressors off on the weekend now. Or you've made maintenance changes. Or you've done capital projects, like you put variable speed drives on a certain system and now its energy usage is lower. Or you've just gained deeper knowledge about the energy usage within your facility through doing other investigations. So you can update the data going into the model. You can also update the distribution in the model. And then that allows it to roll forward continuously. And our customers find that really valuable because it gives them the ability to continuously monitor where their energy is being distributed within their facility. But it also includes the losses. The losses are kind of the last part to it. So we define these 7 types of losses within the model, oftentimes down to very, very fine-grained levels, right down to equipment or even sub-equipment levels for our manufacturing customers, to allow the losses to also roll forward and to be automatically calculated so you can understand where your top losses are, okay? There's, attacking energy losses from an economical sense always means you want to be attacking your top 3 or your top 5, okay? If you're attacking a little loss down here that's your 25th highest loss, you're probably not doing yourself any favors in terms of return on investment or in terms of overall impact to your operation. You always want to be attacking the top 3 or the top 5 losses. So how do we derive these energy losses for the model? There's various means. We start with regression analysis, looking at heating and cooling degree days, production and occupancy, and relating those to your energy profile so that we understand what your normal profile is to your drivers, like HDD and CDD, and then if you step outside of that normal regression, then we know that there was extra losses due to some impact. A piece of equipment failed, or you kept something on when you shouldn't have been. We also use calculations. We look at, we calculate average building heat loss or the required power of the pump that it needs to overcome the head or to move, say 3,000 GPM of water through a system continuously, if that's your requirement. We look at what that actually is going to take, and if you step outside of that, then we consider a loss. Our losses include losses due to technology, okay? If you have anything other than an LED light bulb in your building, it's a loss, okay? There's no question that every light bulb, except for very, very certain specialty applications, should be an LED at this point. So any fluorescence, any incandescence, halogens, sodiums, doesn't matter what it is, that's a loss. Or non-premium motors, okay? I suggest all new motors should be NEMA premium. If you're buying non-NEMA premium motors, you're not doing yourselves any favors right from the start. We also incorporate spot measurements. So high energy use systems will do power flow spot measurements a lot of times, especially on fans and pumps. Averages and baselines, looking at your facility compared to equivalent facilities, looking at the consumption of energy per unit or per unit of production, if that's your driver, or per square foot, if that's your driver, because those are, in the commercial space, it's typically by square foot, and if you're looking at industrial production, it's typically driven by units, not by the square footage of the facility. So looking at those averages and baselines, understanding where yours is relative to everybody else's, everything above the average is a loss. Also looking at the alternatives and renewables that you could potentially generate from your property or what you own, and we'll talk a bit more about that later. And then eventually, we get down to engineering estimates, okay, based on our extensive experience. If there's no direct measurements that have been done or no calculations, we'll put in engineering estimates to define the losses. So what are the 7 types of losses, okay? So we start with the point of use ones, type 1 through type 4, which we define as useless consumption, overconsumption, non-optimization, and recoverable energy. And then we have the systematic types of losses, which are transmission, transformation, and renewables and alternatives. And I will now go through each one of these and give you concrete examples of what each of these mean. So useless consumption. This is a loss that occurs when equipment or a process is on and not producing. So if there's no one in this room and the lights are on, it's a loss, no question about it. If a conveyor is running, but the downstream part of the conveyor is blocked and the parts on that conveyor are not moving forward, that's a loss. That conveyor should not be on if that's the case. Or if I have an oven that's at set point temperature, but I have absolutely no product inside of that oven. It's not functionally, it's not doing anything for me. It's not advancing my value stream. That's a loss. So if we look at this chart here, this is something we typically see. The purple line is where this industrial facility should typically be on a weekend, but this is their actual line. So we define the loss as everything as this area in between the dotted line and the solid purple line. Because this purple line is calculated on, okay, what's absolutely the minimum requirements for your facility just to keep, say, some emergency lighting and maybe your security system running when you're not occupying the building or producing anything on the weekend. And everything else is in between. So this gives you an idea of how much your loss is and where you start to need to attack those losses. So how do you attack them, right? Well, shutting off anything you're not using right away and starting it up at the last possible moment when you need it. That's just standard across the board. That can be accomplished with processes, checklists, schedules. However, we find the human element in terms of energy efficiency or turning stuff off and turning it back on again is not the best control method and probably never will be. So that's when you start to look at intelligent control systems. Even it's just as simple as in a room like this, occupancy sensors to make sure that if nobody moves in here for half an hour, all the lights go off automatically. So those are the types of things that you look at to attack useless consumption. Overconsumption. So this is a loss that occurs when the set points are above the required amount. So some examples are, if I have the heating set point in this building set too high in the winter, or the air conditioning set point set too low in the summer, that's a loss. Okay. Typically, like I don't know if you optimize your temperatures at your home, but if you want to be efficient, you probably shouldn't be heating your home much above 68 degrees Fahrenheit in winter, and probably cooling it to about 78 degrees Fahrenheit in the summer. Okay, but a lot of people don't do that. But if you're outside that range, I would consider that a loss. If you have a conveyor in an industrial facility that's moving faster than it needs to be, if the conveyor is moving faster than the line rate or the upstream or the downstream rate, that's a loss. Or if the lights are too bright in an area that have natural sunlight coming in from windows. So I've now got that basically the lighting output set too high. As we know, LEDs are very very efficient when dimmed. There's definitely ways that you can attack those kinds of overlighting losses too. So how do you attack these? Well, it starts with set point monitoring and management. First understanding what your set points need to be and managing to those set points as well as you can using your computer or your human systems and processes to do that. Then, once you understand you're monitoring and you're managing your set points, then you want to look at optimizing your set points, looking for where your set points can be raised, your set points can be lowered in order to just simply minimize the use of energy. And then, ultimately, you want to look at dynamic set points. Dynamic set points are where it's hands-off, and the system is just dynamically setting its set point. I use the demand flow example. A simple demand flow example is in a process water cooling system. So if I'm sending water out to various processes that may or may not be on all the time, I want to make sure that the pumps driving that water on VFDs and I have pressure-based control out in the loop, so that I'm not just having two pumps run at full speed all the time, because that's my max demand. I want the pressure feedback to the VFDs so they're instantaneously adjusting to provide only the required pressure at the time. It doesn't even need to know what the load's doing, it just needs to know what the pressure in the loop is and trying to maintain that set point. The other example would be, back to the lighting one, would be daylight harvesting sensors. In rooms that do have significant daylight or sunlight coming in, having those daylight harvesting sensors come down. Non-optimization, so this is a loss that occurs when the equipment or process is not using the delivered energy optimally. Examples of this are fan drives where the belts slip, compressed air regulators that are set too high on a piece of equipment, or inverters, internal losses in inverters such as battery chargers or VFDs. You typically attack these. For example, you can use grooved belts instead of V-belts on fan drive systems, which basically transfer all the energy to the belt or to the load. You can minimize energy delivery set points and also use the most efficient equipment and the most efficient inverters that you can find. Recoverable energy is a loss that occurs when a waste stream is not recovered. So anytime I'm sending exhaust air to the atmosphere that has any kind of heat in it, that's a waste. Anywhere I'm piping hot water to a drain, I'm not only losing water, but I'm losing thermal energy as well. And cooling towers. My quote here, this is my quote, I believe every cooling tower that you've ever seen is a waste, right? I'm using electricity to reject heat to the atmosphere. So I'm actually kind of double wasting energy every time I see a cooling tower. Now don't get me wrong, you need cooling towers. Air compressors need to reject heat. Chillers need to reject heat. But instead of putting a cooling tower in, can we recycle that heat into the domestic hot water system instead? Instead of literally using electricity to reject that heat into the atmosphere and contributing to global warming. So you attack these things by enthalpy wheels. Heat recovery ventilation is starting to become almost a standard feature on new commercial and industrial buildings. Air-to-water to air-to-water heat exchangers, so just trying to take hot air or hot water back to hot air or hot water and trying to recover some of that heat. And also using internal diversion. For example, if you have a really hot area of your facility because maybe there's an oven in it, piping some of that air within that hot area just over to another area of the plant to offset some of the heating over there. Transmission losses, so these are a loss that occur when transporting energy to the point of use. So compressed air, any leaks in your compressed air system are a huge loss. When it comes to steam, hot water, and chilled water systems, thermal losses in the pipe, and electricity. The longer electricity wires get, the more internal resistance, the more voltage drop you get over a distance. So, you typically attack these by maintaining the integrity of your energy distribution systems, insulating piping wherever possible, and minimizing the utility run distances, both electrically and for other systems, and trying to really minimize those central utility runs to minimize the piping, and it also saves on capital as well. And I think everybody can appreciate just how inefficient and how much costly fresh compressed air is leaking. This value is really low. This 3/8-inch leak, they say it's going to cost you $12,000 a year, except that's at, hold on a second. There we go. Except that realistically, that's about 3 times as much in Ontario. This is based on 8 cents a kilowatt hour, so that's very, very low for Ontario. It's compressed air leaks are just absolutely horrible. Now, looking at transformation losses. So anytime we transform one energy type to another energy type, we're losing energy. The laws of thermodynamics just simply come into play. There's no way we can convert energy without losing some of it in the conversion process. The classic example is electricity compressed air. Compressed air is absolutely the worst utility, right? It's so inefficient from the time you even generate it. I don't care how efficient an air compressor you have. The best industrial facilities are built without compressed air. They use electromechanical instead of compressed air. But that's not always possible, but you want to minimize your usage of compressed air wherever possible and make it as efficient as possible. Anytime you're turning electricity into chilled water, there's a loss. If I'm taking natural gas plus electricity, turning it into hot water, I also have a loss. How do we attack this? Well, we minimize the energy transformation steps, first of all. So if I'm using gas to create steam, and then I'm using the steam to create hot water, yeah, no, don't do that. Just use the gas to create the hot water and avoid that whole steam step if at all possible. Ensuring that the equipment that is transforming the energy is as efficient as possible. It's modern, variable speed chillers, variable speed air compressors, condensing boilers, and making sure it's as efficient as possible. And also monitoring and tuning up that energy transformation equipment. When it comes to these large pieces of energy transforming equipment, boilers, chillers, air compressors, most of the cost of the life cycle cost of that piece of equipment is not in the initial purchase price. It's in the energy that's going to be used in that piece of equipment over its 20 to 30 year lifetime. So you really want to buy the most efficient piece of equipment you can up front and keep it in good condition. And even if you have to spend a few extra $100,000 at the beginning. And last but not least, renewables and alternative energy. So if you have any potential of harvesting an alternative source of energy that will replace a purchased energy source. So obviously solar, PV, thermal, air, wind and geothermal, and or heat pumps, ground or air source. What you have to think about is that every ray of sunlight and every puff of air and every ground source on your property is yours to be used or is yours to be wasted. Okay? So I can argue that the sunlight falling on your property that's hitting the grass or the shrubs or the trees, let's assume for a second that's useful because we're growing something. But all the sunlight hitting the parking lot is wasted unless you have solar carports. All the sunlight hitting your roof, unless it's covered in solar panels, is wasted. All the sunlight hitting the south and the east walls of your building is wasted unless you're either using it for windows to light the space inside, thus saving on lighting, or you're using a solar wall to collect that solar thermal energy and bring it into the building. So you want to look at what you have, what potentially you have, and you want to maximize your utilization of levels of renewable and alternative sources as best as you can. So just reviewing the loss types again, as we said, the first 4 types are point of use losses. The last 3 types are what we call the systematic losses. So just to wrap it up, so we really feel that this The 7 types of energy losses provides a real framework to cover all practical scenarios. We've been using this for years. We have yet to find an energy loss that we can't quantify into one of these 7 types. So this is what we use to drive these energy audits, these energy cost appointment models, and to help our customers identify where the losses are and assist them in developing strategies to attack them, right? And it really helped provide that focus to tackle the top losses first, and then stratify downward, eliminate losses, and then move on to the next ones. So, thank you for your attention.
Any questions for Josh?
Yeah, so obviously you seem to have mature methodology and the way you consult with your clients and you arrive at cost-saving measures. I just wondered, what were the origins of some of these methodologies? Were they organic to the process? Did you consider lean and agile and 5 whys and other investigation methods?
We use those other investigation methods. One of the big investigation methods that we do use is the Kaizens or the PDCA cycle. Okay, but that is typically more after the fact. So these 7 types of losses, came out of our customer requirements and our customer demands in order to create a structure that really fit, the available, like something that people can get their head around, right? And something that was really practical to attack. So we didn't develop this in a vacuum. This came out of our customer requirements and our customer demands. We just helped them make it practical for their operations and their uses, and to allow them to not only save energy, but also show that they understand their energy and that they understand their losses.
All right. Thanks so much, Josh. Next, we'll move on to Zara.